So this is the last panel before lunch, um, but not the least. We are going to be, I'm Hridesh Rajan from Iowa State University. I lead the discussion on data science at the university and also organize the Midwest Big Data Summer School at one of our leading activities there. Today I'm going to be moderating the session on education. We have three distinguished educators here on the panel. And each of these individuals will be focusing on different aspects of data science education, from undergraduate to graduate to professional data science education. So it is my pleasure to start with Professor Baker. He is an executive director for Indiana State University Center for Autonomous Systems and Applied Analytics.
Okay, thank you. I'm going to not only shift gears, I'm going to change modes of transportation, and that we're going to go into the small unmanned aerial systems and what we do as far as training our students at Indiana State University on being operators of the collectors of data. This is not a commercial for ISU. I just want to let you know where I'm coming from as far as a department, and that typically we're not looked upon as part of data science. The university itself has about 14,000 students, and out of that we have 5 different colleges. In those 5 colleges, the unmanned systems is located in the Department of Aviation Technology and the College of Technology. So we're kind of hidden down in the university. We're not thought of, as I said, as a data science area, and we really came out of an environment which was aviation. It was an area that typically people think about, what are you doing? Are you training your students to just fly drones? And actually, in 2011, we started a little bit early with the fact that it looked like fun. We weren't sure where unmanned systems were going to go. So we actually started with a small grant, bought a vehicle, and said, let's find out where this technology is going to go from the Department of Aviation Technology. And I've actually started learning over time how it becomes a real value add to the rest of the information cycle. It started with a demand for a small minor program. Over time, it developed into a demand for an unmanned systems, a Bachelor of Science in Unmanned Systems. We now have a 4-year degree, and right now 66 students that are enrolled in the major. So it's grown over time. It's an area of real interest. And as I said, the first thing the students come in, they think they're just going to learn to fly drones. And instead, we actually have a department where we're one of the few universities where we're looking at how do you use all 3 kinds of unmanned systems, and that's aerial, land, and water. So we train them in how to use all those. It's like, why do you have a degree? Well, there was a report out by the AUVSI, which is the Association of Unmanned Vehicle Systems International, the largest lobbying body for unmanned systems, and it was 2013. They projected that there would be a growth in industry and jobs of over 100,000 by the year of 2025, and actual economic growth of over $100 billion. So with the growth of the actual systems themselves, the peripherals around it, and the industry jobs, we see that coming on in large capacity now. Where we see a growing demand is on these kinds of industries. This is not an eye test, but I want to talk about a few, and that there are a lot of uses for unmanned systems in border security, real estate, research, firefighting, first responders of all kinds, precision agriculture, areas that are starting to use unmanned systems, and a lot of imagery. So a lot of the talk this morning has been about large data sets. Mostly what we do is imagery. They are large data sets. We can gather a lot of information very quickly. And what we end up looking for are patterns or changes in patterns or changes over time through the imagery to actually impact some kind of an answer that's going to solve a business problem. what we started learning over time is that to provide real value to the information cycle, we had to find the partners on the university campus where they were looking for some kind of research or some kind of problem to solve within their department. So we were able to develop relationships with criminology and criminal justice, the biology department, earth and environmental science, the construction department, other departments that were ready to use the kind of capabilities that we can provide. And we're able to provide sensors that are electro-optical, infrared, multispectral, hyperspectral, and LiDAR, and provide answers to different kinds of research across the entire university. And with those partners, we started looking at how do you support the life cycle and train our students to do that in an effective manner. So the first thing we did was set up a team so where we could go out and actually gather requirements with those individual units, departments, or researchers to determine what it is they wanted to actually accomplish. And then to map to that the actual platforms and sensors that would solve that problem for them. So that becomes our unmanned system department. They go out and they actually collect the data. They fly or drive or actually use some marine vehicles to gather and collect the information, then deliver it back to the individual units who then process the information or the data and turn it into information. We hope that that becomes actionable information that gets fed back into the department, and then from there we also get feedback into our department as to how to improve the process in the future. So did we do it the right way? Did we do it the wrong way? Did we do it high enough, low enough, fast enough, and so on? You'd be surprised how much impact just the method in which the individuals collect the data has an impact on the information that you receive. For example, if you are flying a vehicle over a field and are trying to do some precision agriculture, if you're flying upwind versus downwind, the camera's moving at a different ground speed. So it does affect the data that you receive. So our individuals are taught how to mitigate that problem and handle it and collect the data in such a way that it becomes of value to you. These are the kinds of projects that we work with currently. We are working with companies like Bex Hybrids, Precision Hawk, other companies that do precision agriculture, and we're doing everything from collecting data on moisture in the fields to counting the number of crops or number of plants that come up 2 weeks after being planted in a cornfield. We're doing aerial photography and filming. Working with first responder organizations in emergency response, search and rescue. We have relationships that have been built with local sheriff's departments, police departments, the National Guard, so we're able to go out and work with actual business problems or actual real problems in the world, gather the information, come back and share that information with those organizations in a way that helps solve their problems. Construction is another area that we're looking at. We've teamed up with our construction management teams and some local construction companies and are actually flying over construction sites to do some time-elapsed imagery so that we can actually video how fast things are moving, see what's in sight, do like a punch list to see what has to be done yet, and time the construction of a building. Infrastructure inspection. We're working with the local power companies to do some infrastructure inspection on some power lines, some towers, and some actual smokestacks at the local power plant. So we can actually put an unmanned system inside a smokestack and do the inspection on it without putting people at risk that go up inside there. Natural resources and environmentals, we're working with the local biology department, and we've actually been able to go out and fly to measure the height of the tallest tree in Indiana based on where they were actually doing their research. So these will allow us to put the vehicle up, gather the information, and not put people in harm's way like trying to put them up in a ladder. This is a little bit of project impact. The upper left-hand corner is the picture of an actual flight, an actual area that we flew. It's actually 600 pictures put together to make one. It's an area that's close to you, Beth. It's down a vineyard close to Bloomington, Indiana. It's about 110 acres. Took about 45 minutes to fly over it. And with those, we were able to capture that information, and it gave us about a 5 gigabyte total data in 42 minutes. That was stills. If we'd actually run it as a video, we'd come out over 200 gigabytes. So we're gathering data very quickly with these unmanned systems. Then when we have a problem of how do we store it, the same as everybody else, how do we store it, how do we share it, how do we maintain the security, and so on. The upper right-hand side is one of our individual students who's actually launched a vehicle that did the flight. And the purpose of this flight was to map the area, find out where the moisture in the ground was, and see if we could learn more about the, happens to be a vineyard. So we were looking at how can we learn more about the grapes and the fruit themselves and what we could do to support them. Over a summer period of flying in that area, we actually learned that it was more beneficial for us to just fly and keep the birds away. It saved them a few $1 million in crop improvement because we kept the sparrows and the crows and the robins away. So that was kind of a benefit on the side. The bottom right-hand corner is a city in the state of Indiana. It's an urban training center that it's used by many government and civilian agencies to do first response exercises. And on the lower left-hand side then is a bunch of our students working with a local police department, sheriff department, and National Guard, working on some exercises in first response of a disaster, simulated disasters of earthquakes, floods, and so on. So we actually get our students involved in real-world problems, and they have to learn how to fly or drive these vehicles and match the right cameras or right sensors to get the information that people need. And it's mostly in our areas imagery, and we're looking at things that are relatively short time frame. All right, so in summary, our goal at Indiana State is to train individual operators who know how to solve a business problem. We want them to be effective and as efficient as possible. We are one of the few programs that's actually addressing this from the spectrum of all 3 types of vehicles, air, land, and water. We actually focus on collecting the data and delivering the data in a way that it becomes of value to someone else, and then we want the feedback as to how did we do, how did the process work, was it something that was effective, do we need to change sensors, focal lengths, and so on. We actually had an event where one time we had students who were out flying and they spent 2 days taking pictures that were of absolutely no value at all because they had the focal length set at 12 inches instead of 1,200 feet. So there are some things they have to learn along the way. We're also looking at remote sensing for small unmanned vehicles is becoming something that's going to be of real value to many industries, from real estate and so on. And that integration of our data cycle is for the entire information cycle is really important. It's an area of research that needs to be looked at, and we need to be considered on the front end. How many of you today really think about where your data comes from rather than just it appears and you're using it? So we want to be included in your planning processes in the future when it's appropriate for you to use an unmanned system. So thank you for having me here today, and I'll be around for questions later.
So our next speaker, Beth Paley, she's a professor at Indiana University. She directs the Data to Insight Center and serves as scientific director of the Pervasive Technology Institute. Beth?
Hello, everyone. It's great to be here. Beth Paley. I'm a professor. I'm also chair of the curriculum committee for the data science program. I don't want to necessarily tell you about our data science program, but I do want to tell you how we're thinking about it. And then I want to segue that just really quickly into how that might influence our thinking in the Midwest Big Data Hubs about leveraging each other for shared advances in data science workforce training and data science education. And I like the specific targeted approach you're taking at Indiana State. I think that's powerful. So the School of Informatics and Computing is about 100 faculty strong, and it's across 4 units: information library science, computer science, informatics, and intelligent systems engineering. So it's a large entity on campus. The motivating goal for data science education, as many of us are thinking about, is the job shortages, projected job shortages. Based on some numbers, there's a projected shortage of somewhere under 200,000 people that have deep analytical skills, and then a shortage that's significantly larger for and Fenn called it, I think, the what did she call it? Action, knowledge to action, which I think is yeah, that was knowledge to action. Yeah, I thought that was a nice way of characterizing it. And those people are significantly, significantly in more demand. I'll go into a little bit of detail about what that means because I think it's important. I come from a computer science background, so I am a deep analytical person by nature. And it's also a high-paying field. So, so our data science program started at whatever, looks like we started tracking it in fall 2014. You can see by the curve it's growing pretty precipitously. That's broken out by online and residential, and the residential has grown over the last, looks like 6 months even, and the online has also. And we're drawing from, we're drawing from courses that we have. And like many of us, it's like, okay, we got to get a master's degree out. What are we going to do? We're gonna grab a class here and a class here and a class here, and we're going to call that a master's degree. And that's all perfect for the first year or two. And then if you don't really think about what you're doing and do something a little more intentional, you're not serving your audience. You're not serving the students. So we're at that point in the program right now. We're stepping back and saying, whoa, kind of gobbling together a curriculum is not necessarily the most intentional way of doing things, and how do we think about it? So what we're doing now is stepping back and thinking about it a bit. And we're doing it in the context of personas. The academic world uses these personas to figure out how to appeal to certain student groups when they apply in their freshman year. So these student personas, they're a representation of goals and behavior of some hypothesized group of students interested in, school, interested in some form of education. So we're focusing that on what the data science persona might be, and we identified 3 of these student personas, and we're targeting 2 of those, and I'll spend a little more time talking about the 2 now, and the third I'll less so. But 2 of those personas for the master's degree, and then that third persona we're looking at trying to satisfy by certificates at cross campus. So this deep, this student persona number 1, deep technical. They've got quantitative strength, that is, calculus-based, probability-based, strong statistics, discrete math. Evidence of not only strong programming skills, but for goodness sakes, interest in programming. And coming out of computer science, it's like, well, if you don't have an interest in programming, forget it, which is fine. That's how I came up. But there is a wealth of people, and I'm sure you can relate to this, that are doing analytical things that don't want to be deep technical programmers, and that's okay, and they can still be extremely productive in a research world without being programmers, for goodness sakes. And their computational skills, their computational thinking skills are obviously good. Okay, then there's this second persona, which maybe you could call this the knowledge to action. These people are also quantitative in their orientation. It may be non-parametric statistics, finite math, strong computational thinking skills here, but just not that interest in programming. And the need here is the application of analysis tools to specific problems facing something like an industry. So interpreting results, visualizing results, basic skills at managing and cleaning data, making forecasts. So much of what we're doing now is forecasting for whatever our particular application. And then also selecting technology for big data computing. So much of what we're seeing now are data sets growing larger and larger. And if you don't have the, if you can't distinguish a MySQL database from a Cassandra database, you probably have problems in navigating your way through a big data problem. And then finally, there's this third persona that is certainly evidence on our campus, and I think it's evident on other people's campuses also. And these are people that are coming out of disciplines, what do we call them, science, scholarly disciplines, who have computational thinking skills. Also, again, weak interest in programming, and both quantitative and qualitative. Their strengths, their methodological strengths may be quantitative or qualitative. And these people see themselves learning enough about data science to go back into their disciplines and bringing about effects in their discipline. So here again, visualizing results, basic skills at managing and cleaning data, applying data mining tools to a particular problem. So again, because so much of data science talks about the mining tools, the deep technical person writes new algorithms. The other two personas are able to distinguish the application of tools in certain cases. And that application of tools in certain cases is a non-trivial problem and requires a deep understanding of the computational aspects of what's going on. They're just not programming new tools. So there's that split there. So, as we're thinking about this, and we actually brought this as a poster because I like the way of thinking about it, and it's the top is the degree, the bottom's where you start. You climb the mountain, and I've spent quite a bit of time in the research data lines that came up in the first panel, and I chaired the technical advisory board. A couple years into RDA, which is a grassroots group trying to facilitate research data sharing internationally, there were 54 interest groups and working groups. I did a clustering activity across that to look at where that activity lied. Were the working groups trying to solve social problems, social organizational problems? Were they trying to solve technical problems? The other dimension was, were they trying to solve it from the perspective of the data provider or the data consumer? I was very, very surprised to learn that half of the activity in the Research Data Alliance is in that social organizational dimension. And I was quite surprised by that. And what that tells you are the technical issues are equally as large or small as the social organizational issues. And that bears out, my experience bears that out. This mountain bears that out also by casting across the bottom. I don't know how clear you can see this: data management, databases, text and data mining, data visualization, big data analytics, statistics, some programming dangling off of the woman's hand there. And then in the social organizational space, digital design, open data, we talked about here, storytelling. If you're going to tell a story with data, be good at telling stories. Programmers are not good storytellers. That tells you there's a divide right there. Programmers tell stories with code. Data reproducibility and trust, data curation, critical issues. And then on top of that, and I think this is a key aspect, and this is how we're thinking about it, and I think, Richard, I think you're thinking about something similar, is leveraging whatever those assets are at your university that are unique. And in our case, we've got assets in, I think I've got them right here, we've got assets in HathiTrust. We're sitting on 15 million digitized books and providing 5.2 billion pages, providing text mining and information retrieval access to that content. We're digitizing our film and video on campus, and all of it actually, which is petabytes upon petabytes of information. And then the Network Science Institute, which is pulling together research data sets for research. So you pull these things together and you say, okay, the ultimate experience in that program is this capstone experience. And by the way, we're leveraging our own data assets on campus to provide that experience. So just running through the last of these slides very quickly. So what might this trajectory through up this mountain look like? Well, for the persona number one, who's the deep technical person, they spend most of their time at the bottom part of the mountain, but they still go through some of these social organizational issues. And this is where, this differs from, and it goes through a capstone, and this is where it's fundamentally different from something like a computer science degree or an informatics degree. And then if we look at, and again, my hand art had to come in here, but the persona number two is going to spend more time in the social organizational piece of this, less time in the technical, still coming up through the capstone. And then, thinking about what that third person that's going to go back into their discipline, what is it that they need? And for them, it may be more intensive, focused efforts around data within their specific area with smaller, a little less skills in the technical and the social organizational. And again, you pull all that together. And again, these are conversations we're having right now. And I found this diagram useful for thinking about these kinds of things. And I'm hoping at the poster session we can talk more about this. But this is the thinking that's going on right now as a way to bring focus and order to our existing data science program. And I just want to leave you with this. This is a conversation Melissa and I had. The Midwest Big Data Hubs has an opportunity to gain computational resources and storage resources on Azure, which I think is wonderful. We could look at that same notion of projects. What are these data sets? And we pull them together on one of our spokes. Ag is a spoke that there's has some potentially has data sets of interest. I think IUNI has the network science spoke has potential data sets of interest. We put them on Azure, and then now we form whatever our curriculum activities are, and data use agreements are important here, and licensing and restrictions on data have to be worked out here. But we make these available then so that we can begin to share curriculum. And we're not forming our own certificates. We're not going to take that on, or our own master's degrees. But we do, I think, have shared workforce needs that we can collectively harness Midwest Big Data Hubs to solve together. So thank you.
Our next panelist is Professor Alex Smith, who is going to present a unique program. I think Alex serves as a chair of the mathematics department at University of Wisconsin-Eau related to this role, he has collaborated with faculty from other UW campus to plan, develop, and implement the UW online master's degree of data science program, which is across campuses. Thank you.
Thank you. Let's see. I want to describe the University of Wisconsin Data Science Program. It's a Master of Science degree, and it's completely online, 36 credit master's degree. And it consists of 12 courses, 3 credits each. And it's a partnership with 6 campuses in the University of Wisconsin system. And then there's this other entity, UW Extension, which is sort of the administrative glue for the whole program. So the University of Wisconsin system has 13 four-year campuses. Those are the stars with circles around them. And then it also has some 2-year campuses. Those are the stars. The 2 R1 campuses in the system are Madison, of course, and Milwaukee. They're not in the partnership. And so then of the remaining 4-year campuses, 6 of us have partnered with UW Extension to put this master's degree program together. And so the 6 partners are Eau Claire, La Crosse, Stevens Point, Oshkosh, Green Bay, and Superior. And then, of course, UW Extension. So let me indicate who is enrolled in our online master's degree program. This semester, we have started our 2nd year of delivery. It's primarily adults working full-time, many with family obligations, and the average age is 37. So I'm used to teaching undergraduates primarily, and so by my standard, these are a very different population for me to advise. This fall semester, the average number of courses taken by a student is 1.6. We tell students a full-time graduate load is 9 credits, but you know, you're working full-time, you have family obligations, take 1 or possibly 2 courses at a time. And currently we have students from 33 states and a few international students. 68% are from what you call the Midwest Big Data Hub states. Of course, a big chunk of those 68 are from Wisconsin and Minnesota, I think. So the basic structure of the program, a student selects one of the 6 campuses as a home institution. And then at that home institution, we deal with the admission of the student, financial aid, advising, academic policies, you know, good standing, academic warning, all sorts of things. And then the actual granting of the degree will be from the home campus that the student selects. Each campus teaches 2 of the 12 courses, and they're online, of course. So the student doesn't really perceive, it's not an obstacle that someone is teaching a course at La Crosse and the student has picked Eau Claire as a home campus. It's pretty much transparent. UW Extension down in Madison coordinates course development and delivery. They're very good at course design. They do the marketing, the finances, and they bring the campus academic people together for collaboration and planning. So the curriculum is a fixed 12 courses. There's a survey course, DS 700, and then statistical methods and programming for data science. We quickly learned that we should have renumbered these. We decided now that the programming for data science should be taken before the statistical methods course. But we're locked into this illogical numbering system now. Data warehousing. Pretty much 700, 710, or 715 are courses that a beginning student can take. Ideally, they would take 700, but if it's full, then they can take 710 or 715. We have a high-performance computing course, big data. And then communication about data, telling stories. Course in data mining and machine learning. Visualization and unstructured data. An ethics course. That's a very critical course in my perspective. And remember, all these courses are required. Prescriptive analytics, strategic decision making, and then finally the capstone. This coming spring semester, I believe we'll have our first students in the capstone. And so we're dealing with the logistics of that at this point. Some of the challenges, well, when we came together, like we had to figure out what is data science. You know, you think, oh, we'll just go down and put together a curriculum, and then you get together and you realize, well, that's a hard question. What is it? There are technical software challenges for online courses, but then for this discipline, there are even bigger technical challenges. And so we settled on a virtual desktop. Another challenge is working with non-traditional students who are entering a graduate program after several years out of college. You know, these are real courses, they're not MOOCs, and I think so often we fall into the idea, well, a MOOC, I can start it and I can quit, you know, that's what mostly happens. But when you're starting a graduate course, you have to remember you've got to stick with it. So, you know, there are rigorous academic expectations, and so coupled with the inherent difficulty of the subject, this is a challenge to deliver it to this audience. Another challenge is the fact that we're 6 campuses and we have to coordinate to some extent our academic policies, grading policies about academic standing, that sort of thing, calendars, academic calendars. Some closing thoughts on our collaborative model. I don't think any one campus would have had the brain trust to put this program together. You know, there'd be some computer science people from one campus and statisticians from another, and business administration people from another. And when we got together, we had the right mix of people to teach. The interdisciplinarity of the subject really emerged naturally from this collaborative model. It forced the fact that the curriculum is not housed in one discipline, in a computer science department or a math department or whatever you might have. It really, the way it came together, the interdisciplinary was forced upon us. Of course, we wanted that, but it was forced. And I think that the course design and expertise from people at UW Extension, coupled with the UW system faculty across the 6 campuses, really have come together to provide a very rigorous high educational opportunity for a non-traditional student. So, thank you.
So we are happy to take a few questions here. Please.
So, I'm not just speaking for all of you, but maybe particularly with that, if you find that there are students who, you mentioned this persona 3 is right, like having people that need to, especially in this area, but they're already coming in with knowledge, they're really specialists in some other area. Do you find that there are people even who just want to pick up 1 or 2 courses, and then in that case, like if you want to integrate big data into your other disciplines, like you are with UAS, what's the most important thing that they need to learn?
This is a religious argument, you realize. I happen to teach data management and data quality, and and again, allow me, because I think most people would say, if you can't pick the right analysis tools, you're not going to be effective in applying them. And I think there's a skill there. But I think there's also a gap in people recognizing that if the data isn't in the form you need and in a form you can trust, it doesn't matter what tool you pick. So I think those precursor issues of pipeline, attribution, trusting are absolutely critical. Because again, I think right now we're focusing on the mining, and we're taking Irvine's simple data set and using it over and over and over and over and over again because there are no other data sets. And what that suggests is downstream is where the problems really are. So I think both are critical.
I think from the unmanned system side, as we became involved with other departments, construction, biology, criminology, and so on, from that, we started learning that the whole life cycle of the information was absolutely critical. And I've been asked to look at bringing online a Master of Science in Analytics in the next year that's interdisciplinary based on the work that we've already done in those departments, so that we can capture information from the very front, being the unmanned systems, and feed it through that data processing, storage, and so on, and then the actual use. So I think that the understanding of the life cycle itself, not just one piece, not just data mining, not just processing, not just collection, but the whole thing of the entire life cycle is important.
Yeah, I see this is interdisciplinary, programming, statistics, communication. So I think my answer would be to take a course in that area that you're not familiar with.
I was curious on Wisconsin, the platform that you're using for your online courses.
It's virtual desktop. What's the standard one now? I'm drawing a blank.
VirtualBox?
No.
No? Okay.
Yeah. It's a virtual desktop. I've forgotten now. The extension uses it. One of the interesting things about that is with the course designers, you have to get straight with them. Well, you don't have to put R on that, but you can put many things right on your local computer. So I'll remember the platform in a minute.
So I can answer that from the IU perspective, but so our university is using Canvas as a course management system, and we said we wanted to use edX because we like the flexibility, and for security reasons, the student identities have to remain in Canvas. So now we've got that. So we've got edX, and we're using Piazza for our communication. We're using Zoom for our interaction with the online students, and frankly, some of the residential students in some cases. And that pairing of platforms, and then we're using national resources, we're using Jetstream and virtual machines there for our project. So, I mean, it is trying to reduce the total platform footprint is important, and we're not quite there yet. When my AIs threw in TAs and threw in Box, I said, wait, no! We're pushing our students over the edge with platform proliferation. So that is a critical issue.
Yeah, we do use D2L and as a learning management system, but to give students access to proprietary software. That's where the virtual desktop comes in.
Yeah, we're using ArcGIS, Data Mapper, Terra Server. Some other things are specific to the imagery environment, mostly in the cloud.
More questions? Yes, Nick?
What role does the industry play in the curriculum design? Because essentially they are the end users of the educational system, at least one big user, right? And ideally they should participate in the curriculum design, maybe give some guidelines on the tools that they want or the skills that students must have. So how did you go about this thing while developing your curriculum?
From our point of view, our industry partners have been involved from the day one so that we can actually put together a curriculum that met their needs. Not only just the curriculum, but also the software platform that would support their actual imagery needs also. So we had people from the government, people from industry, and other academic partners at other universities that were involved.
I mean, so this is a long kind of, in academia, you're probably familiar with this, we talk about this a lot, is, what tools and what skills, and the skills, ideal, if you're teaching kind of these foundational concepts, then they can apply them to, if you're teaching them distributed systems or distributed storage skills, they can apply it to Cassandra versus Redis versus, whatever the particular platform is. So, we try to back that off a bit so that we are giving these skills. And then as far as feedback, your older students will give you good feedback themselves, and I think that is valuable. But we tap into the School of Informatics and Computing, we tap into their connections, their career connections for that feedback. And a lot of that feedback is not necessarily in tools, it is in, the ability to communicate. And in some of these softer skills that technical programs usually have a hard time delivering on.
And UW Extension puts together an advisory board of nonprofits and businesses and government agencies in Wisconsin. And that really informed the curriculum, and as we move on, curriculum reform with this advisory board.
Okay, so I think we are out of time, so I don't want to stand between you and your lunch any longer. The panelists are here for a little while, so if you have any follow-up questions, please direct them to them. All three of them have leading unique and interesting programs. Thank you very much for your participation in this panel.